Welcome to The Last Breakfast. Please enjoy the video.
In this video, I will explain how to use a low-pass filter. Let's dive right into understanding this fundamental electronic component. A low-pass filter is an electronic filter that passes signals with a frequency lower than a certain cutoff frequency and attenuates signals with frequencies higher than the cutoff frequency. It's essentially a frequency-dependent voltage divider, allowing lower frequencies through while blocking or reducing higher ones. This is crucial for cleaning up signals and removing unwanted noise. Understanding how a low-pass filter works involves its core components, a resistor and a capacitor. These two elements work together to create a frequency-dependent impedance. As the frequency of the input signal increases, the capacitor's impedance decreases, effectively shunting higher frequencies to ground. The point at which the output power is reduced by 1/2 or 3 decibels is known as the cutoff frequency, calculated as 1 divided by 2 pi times the resistance times the capacitance. Low-pass filters are incredibly versatile and find applications across many fields. In audio systems, they are used to direct low frequencies to subwoofers, ensuring clear bass reproduction. In signal processing, they smooth out noisy data, removing high-frequency interference that could obscure important information. For power supplies, they filter out high-frequency ripple, providing a stable direct current output. They are also essential in anti-aliasing filters before analog-to-digital conversion. Designing your own low-pass filter involves selecting appropriate resistor and capacitor values to achieve your desired cutoff frequency. For example, a 1 kiloohm resistor and a 1 microfarad capacitor will yield a cutoff frequency of approximately 159 Hz. Consider the input and output impedance of your circuit to minimize loading effects. Always test your filter with a signal generator and oscilloscope to verify its performance and ensure it meets your specific application requirements for optimal signal integrity.
Thanks for watching. If this was helpful, leave a like and consider subscribing. See you next time.